Então, o tema central dessa workshop seria tecnologias para aumento de capacidade e monitoramento de ativos na distribuição e transmissão. A gente consegue permear as duas áreas de negócio do setor elétrico, uma vez que linhas de transmissão, dependendo do nível de tensão, está ou na distribuidora ou na transmissão. O programa de apresentação, a gente começa com as partes técnicas a 9h30. A gente convidou um representante de uma empresa americana, a USI, é o senhor Gerhard Biedman. Ele vai fazer uma palestra na língua inglesa, falando sobre o estado da arte em tecnologias de monitoramento, buscando aumento de capacidade de linhas aéreas. A gente faz um intervalo na sequência. Na sequência, o pessoal da UFMG vai falar sobre monitoramento ambiental de linhas aéreas, alguns resultados obtidos com o projeto e já um pouco de proposta de continuidade desse projeto. Na sequência, 2 professores da UFMG irão falar um pouco sobre sistemas e teste em túnel de vento para explorar mais o ativo existente de linhas aéreas, com foco no ativo existente e no ativo que será construído no futuro. A gente para o almoço. Na sequência, o pessoal do CPQD vai falar um pouquinho de como é a nossa visão dos sistemas ópticos nessa área de monitoramento de ativos. Aí a gente tem uma sequência de tecnologias de ruptura, uma vez introduzindo a fibra ótica junto do cabo de energia, que a gente ainda não consegue prever todos os ganhos que existem nessa aplicação. Aproveitando essa área de fibras óticas, que é uma coisa recente no setor elétrico, a gente já conta no Brasil com um fornecedor, que é a Minipa Sense, e nós convidamos o palestrante Victor Diego, que é diretor-geral de tecnologia da América Latina, irá apresentar algumas tecnologias que já estão no mercado, né? Você já pode fazer a aquisição dessa tecnologia para uso no setor elétrico, também com foco em monitoramento de ativos. A gente faz mais uma parada para café e água. E a última apresentação está focada nos supercondutores para uso em sistema de potência. A gente tem uma conclusão do projeto no final de novembro, que é um marco tecnológico para o Brasil nessa área de supercondutores, e a Cemig e as empresas que financiaram esse projeto têm bastante orgulho de poder estar apresentando isso no Brasil. Também o professor Arthur e Marcelo irão apresentar um pouco dessa tecnologia para a gente. E a gente vai terminar sagradamente às 17 horas. O assunto não se esgota, ele é amplo, mas a gente vai abordar os pontos focais do que é mais importante para a gente pensar no futuro com essas tecnologias. Basicamente, se vocês me perguntarem assim, quais são os motivadores do projeto, teve um plano estratégico? Eu falo, não houve. Houve sim uma coincidência de fatores que pode demonstrar que existe uma lógica no desenvolvimento desses projetos em conjunto. Depois que os projetos foram executados, a gente consegue dividir ele em 3 grandes camadas que estão apresentadas aí nessa apresentação, que seria a eficiência dos ativos de transmissão e distribuição que estão em operação, como fazer uma convivência com a sociedade desses ativos, né, que eles estão presentes aonde que a sociedade convive, né, que é o nosso planeta Terra, e como poderia ser a expansão desses ativos de uma forma não convencional, do que já se vem fazendo há 100 anos. Né? Então essas 3 figuras mostram que a gente tem no mundo muito ativo de transmissão e distribuição. O que a gente pode ainda tirar de vantagem desses ativos para a sociedade e para as empresas? Então, existe uma série de tecnologias, uma série de estudos que podem ser elaborados. E dentro dessa linha, a gente vai apresentar o que a gente fez. Partindo da Europa, existe hoje uma restrição muito grande na expansão do sistema elétrico. Então, a gente observou, através de um outro projeto, que é possível você buscar uma aceitação melhor da população frente a essa expansão. E essa figura, a última aqui, mostra um pouco de um contexto não só brasileiro, mas principalmente dos países em desenvolvimento, das características das redes existentes. Pensando no futuro, a gente não imagina isso aqui por muito tempo, né? E quando se fala em expansão dos ativos, a gente tem que, talvez, com muita propriedade, tentar fazer diferente. Dessa forma aí, não parece ser viável. Eu trouxe uns números aqui, só para a gente pensar em algumas informações. Quando a gente fala em ativos, né, seriam as linhas, as subestações, os cabos, as torres, todos os equipamentos de supervisão. Fizemos uma distribuição aqui em transmissão, subtransmissão e distribuição, que coincide com o que é hoje a Cemig. A Cemig tem 10 mil quilômetros de linhas acima de 230 kV. Ela tem 16 mil quilômetros de subtransmissão, que seria até 161 kV. E na distribuição, a gente tem 500 mil quilômetros de redes. Colocando alguns números mágicos nessa financeiros, é como se tivesse hoje um valor de 3 bilhões a rede da transmissão, 4,8 bilhões a subtransmissão e 12 bilhões. E fazendo uma conta simples, que esse ativo já está depreciado 66%, a gente teria hoje um valor de mercado de 7 bilhões na Cemig com esses ativos. Continuando o raciocínio, supondo que a Cemig é 10% do Brasil, o Brasil tem 100K, 160 mil quilômetros e 5 milhões de quilômetros de rede de distribuição. Seria um ativo de 70 bilhões. E se a gente supor que o Brasil é 10%, né, da economia da China, e se isso refletir no ativo, a China hoje tem 10 vezes mais e teria 700 bilhões em ativos em operação. Então, esses números não estão corretos, somente apontam o rumo de como que a eficiência dos ativos de transmissão e operação é importante a gente desenvolver pesquisas que tornem esses ativos mais eficientes. Por exemplo, se a gente conseguir otimizar esse camarada em campo aqui, né, que já tem mais de 100 anos que está em operação e praticamente da mesma forma, a gente conseguir explorar 10% da capacidade original dele, a gente pode ver aqui um ganho de 700 milhões, aqui de 7 bilhões e aqui de 70 bilhões. Então, são valores econômicos muito considerados. É essa linha que traz uma motivação para a gente. E nessa área de eficiência dos ativos, a gente vai contar com duas apresentações do mercado, que seria essas tecnologias de aumento de capacidade, a gente chama aqui Real Time Monitoring, monitoramento em tempo real, vai ser feito pela empresa USI, pelo nosso colega Guerra. Ele vende equipamentos e software que prevê, a partir do monitoramento da temperatura do cabo, qual a capacidade da linha. E isso a gente consegue ter aquele ganho de eficiência do ativo. A gente vai mostrar a apresentação da Minipa, tecnologias ópticas que ajudam o monitoramento, a parte de automação dos nossos ativos. Aqui, por exemplo, uma invasão de um muro, por exemplo, é detetado por uma fibra ótica e isso é alarmado no centro de controle, dentre outras aplicações que ele irá mostrar. Na parte de dois projetos, com a UFMG, o 310 e o 309, a gente vai mostrar, associar tecnologias de monitoramento em tempo real com processamento da camada limite do vento. Foram estudos que nós já elaboramos desde há 10 anos atrás, que por coincidência hoje o mundo todo sinaliza essa possibilidade de fazer essas correlações para a gente tentar localizar onde são os pontos mais críticos de resfriamento ou de aquecimento dos cabos condutores para você poder aumentar a capacidade do ativo existente com segurança. Mas, por outro lado, ainda existem muitas pesquisas a melhorar a superfície do condutor, a tornar ele autorrefrigerado, vamos dizer assim, que você consegue, além de aumentar a capacidade de transmissão, reduzir perdas do seu sistema. E muita simulação pode ser feita usando o túnel de vento. Esse é o exemplo do investimento que a gente fez no UFMG. O professor Rudolfo vai mostrar um pouco do que ele pensa para o futuro, dos resultados que ele obteve estudando a superfície do condutor. Basicamente, a gente tem aqui, por exemplo, materiais novos, nanotecnologia que pode ser aplicada, por exemplo, abstraindo o conceito por um robô, a gente pintar os condutores e tornar ele 20% mais eficiente. É claro que existem várias restrições para fazer isso, mas na dimensão da pesquisa é o que a gente está buscando, é o que a gente está investindo. E mostra o primeiro projeto que o CPQD começou com a Cemig há 14 anos atrás, que ele consolidou no lote pioneiro de uma tecnologia de monitoramento óptico, que é esse sistema que monitora a força. Ele tem uma série de vantagens, porque ele é passivo, ele não precisa de energia, ele reflete a luz aqui, e ele usa a fibra ótica como meio de telecomunicações. O Cláudio vai mostrar isso para a gente. Então, assim, nesse sentido, a gente busca a eficiência, né, numa rede muito grande que existe hoje na Cemig, no Brasil e no mundo. Então, são pesquisas que têm um objetivo de trazer um ganho operacional, com uma eficiência operacional para as empresas do setor elétrico. Pensando naquela convivência com a sociedade, a gente tem três fatores que estão ocorrendo. Aquele que eu já comentei sobre aceitação. Essa aqui é uma figura que foi buscada da Bienal de Paris em 2014, mostrando na Holanda um pasto aqui, né, que as pessoas jovens escreveram aqui, ó, não queremos poste aqui. Então, é um processo de convencimento muito grande. Por outro lado, a gente tem uma expansão muito considerável do sistema e a gente tem que fazer uma operação segura. Essa foto recente mostra um acidente numa fazenda lá do Rio Grande do Sul. Infelizmente, acho que 28 vacas morreram quando um condutor caiu sobre elas numa tempestade. Então, se a gente encontrar tecnologias que busquem melhorar a aceitação da expansão do sistema e o ativo existente possa se tornar, ou futuro, mais seguro, essa é uma meta, né, um objetivo muito forte que nós temos que buscar. E numa terceira dimensão, que seria as novas gerações, como que nós conseguimos captar a atenção dessa geração, que a gente chama geração Y, né, para vir para o setor elétrico e para trazer novas formas de desenvolver tecnologias e que, ao mesmo tempo, a gente deixe um legado para elas de uma área de transmissão e distribuição mais a cara deles. Então, falando assim, bem pé no chão, se as nossas redes não forem inteligentes no menor tempo possível, muito dificilmente essas pessoas virão trabalhar no setor elétrico. Por outro lado, quanto mais digital for o setor de distribuição e transmissão, maior a chance da gente captar a atenção dessas pessoas mais jovens, porque elas já nascem conectadas, elas não têm menor condição de estar desconectada, principalmente onde elas vão trabalhar. Então, é uma dimensão muito crítica que tem que ser trabalhada rapidamente no setor elétrico. E os projetos que a gente vem desenvolvendo de mostrar os ganhos de aplicação do controle, de colocar robô para tomar decisão, né, de monitorar uma rede, vão nessa linha numa última instância. E aí, o grande foco seria desenvolver novos relacionamentos entre a empresa e a sociedade. Nesse sentido, a gente teve um projeto bem interessante, que foi com a FMG também e outras empresas de tecnologia. Desenvolvemos um sistema de monitoramento de imagens, que essas imagens vão para a internet, e a sociedade ela tem um papel de poder contribuir com a preservação ambiental. Fala assim, olha, estou vendo foco aqui, eu mando uma mensagem para o Corpo de Bombeiros. E como que a gente percebeu que isso foi importante? Pela repercussão que o projeto deu na mídia em 2014, quando Belo Horizonte foi atacado por vários incêndios muito próximo da população. Então a gente observou que uma nova forma de abordagem de tecnologia com a sociedade pode trazer grandes ganhos para as empresas do setor elétrico. Aqui é um caso real que o professor René e o Douglas vão mostrar, de um incêndio que ocorreu dentro da UFMG, e a tecnologia desenvolvida já consegue detectar e mostrar aqui o foco de fumaça e alarmar o Corpo de Bombeiro, a Defesa Civil ou o centro de controle, né, uma rede mais próxima. E na outra dimensão, que a gente atua também nessa convivência com a sociedade, é a gente imaginar que o futuro do setor elétrico vai ser dominado pelas máquinas, né? Machine to machine, M to M. E o grande operador do sistema, que é um ser humano que processa bilhões de informações por segundo, também será dessa forma representada por bilhões de dados de equipamentos operando em tempo real. E nesse momento, a sociedade pode ser muito beneficiada com a criação dessas redes inteligentes, se a gente pensar em banda larga para todo mundo no Brasil. Então, esses projetos, o 520 e o 566, a gente deu o nome de rede sinérgica. A gente tem uma rede muito robusta no futuro, que vai ter energia com muita qualidade e banda larga de sobra para a sociedade poder usufruir isso também. É uma ruptura tecnológica do ponto de vista da aplicação, da especificação dos equipamentos, das patentes, de como o setor elétrico irá trabalhar no futuro. E é claro, a gente está aqui em 2016, a gente tem uma visão de como é o mundo, por exemplo, uma pessoa pode enxergar uma visão de satélite, como grande parte da nossa geração pode lembrar daquele mapa mundi lá no grupo que a gente via o mundo daquela forma, mostrando como que a mesma coisa pode ser tão diferente do ponto de vista de duas pessoas. E com esses projetos nós estamos observando que o engajamento com a sociedade vai ser fundamental para o sucesso desses projetos. Pensando no futuro, na expansão dos ativos, a gente tem aí uma oportunidade fantástica de fazer diferente. Mas, se a gente não conseguir provar financeiramente e tecnicamente que é melhor, esse camarada aqui continuará dominando. Há 100 anos ele vem sendo utilizado. E se as outras tecnologias não mostrarem vantagens, ele continuará sendo utilizado em larga escala nos próximos anos da expansão. Do ponto de vista nosso, a gente já tem hoje produção de cabos com fibras óticas, por exemplo, que vai trazer uma rede inteligente. Aí a gente vai chamar aqui de Optical Phase Conductor ou Optical Distribution Conductor, depende do nível de tensão. Aí realmente está mostrando, não só no Brasil, mas no mundo, uma baita oportunidade do setor elétrico fazer expansão somente com esse tipo de condutor. Na Cemig-Distribuição, na área de planejamento, eu já coloquei para as pessoas de planejamento a importância de a gente pensar nos próximos, a gente vai desenvolver 1.600 quilômetros de novas linhas, já pensar fazer tudo com esse condutor. Mas eu entendo que não é fácil, não é trivial você fazer essa mudança. É aquele ditado popular, para que nós vamos mudar, né, o time que está fazendo gol, o time que está ganhando? Mas a gente não sabe até quando o time vai continuar ganhando com essa tecnologia que começou em 1900 com um cabo lançado em Nova York. Depois ele virou alumínio. Houve uma ruptura tecnológica grande, porque você conseguiu construir vãos maiores. E naquele momento as pessoas, acho que quem usava o lampião, a querosene, nunca imaginava que ia ter um fio chegando na casa deles. E agora a gente está no momento de pensar o seguinte: eu tenho um sonho que é chegar uma banda larga na minha casa. Esse é o futuro, eu acredito nisso, é isso que eu tento passar para os nossos parceiros. Se o Brasil investir em banda larga, em larga escala, nós temos uma mudança na nossa economia. E essa mudança, ela pode ser muito benéfica para as próximas gerações. Bom, mas se a solução não for utilizar essa possibilidade, a gente ainda tem como avançar muito em cabos subterrâneos, né, com cobre e alumínio, mas aqui já existe o consenso que todas essas redes subterrâneas já estão nascendo já com fibra ótica. Ufa, muito bom. O pessoal já viu a importância da banda larga junto do setor elétrico. E mesmo assim, para vocês terem ideia, a energia que é produzida em Itaipu hoje, 12 GB, 5% dessa energia fica no meio do caminho, que são usando esses cabos. Se eu usasse uma tecnologia, por exemplo, como supercondutores, que são fitas que não têm baixíssimas perdas elétricas, eu poderia salvar uma usina de 600 megawatts, 5% de perdas. Então, o que está em jogo, né, por trás dessa tecnologia são muitas variáveis que a gente talvez não consiga colocar a mão. Mas quando você faz uma análise financeira, fala assim, olha, realmente tem mercado para a tecnologia. E a Cemig vem buscando atuar de forma a conhecer a tecnologia e preparar o futuro, preparar para as próximas gerações. Nessa linha de supercondutores, que vai ser a última apresentação, o estado da arte são fitas com capacidade de condução 10 vezes maior do que a mesma seção em cobre. É uma ruptura tecnológica. Mas ainda a gente tem alguns desafios que a gente chama esse aqui, cabo supercondutor em alta temperatura. O alta temperatura para a supercondutividade é menos 200 graus Celsius. Então, a gente aproximar da temperatura ambiente, essa característica de supercondutividade, que seria a grande revolução industrial ou tecnológica da área de supercondutores. Então, assim, para garantir uma expansão de transmissão e distribuição, a gente vai ter um leque de possibilidades para poder testar, poder colocar em operação, aprender, errar e ir fazendo, e fazendo, e fazendo, e fazendo, e fazendo. Essa é a tônica. Não vamos deixar que esse camarada domine o nosso futuro. E pensando em supercondutividade, né, só uma representação de motivação. Quando a Embraer era esse avião fantástico aqui, em 1970, eu acho que o mercado não acreditava que a gente chegaria como terceiro do mercado com essa aeronave fantástica, né? E o sonho se tornou verdade. Aqui também, supercondutividade. Nós temos um grupo de investidores e um grupo de pesquisadores que acreditam nisso, que a gente consiga ter uma aplicação dessa tecnologia em área comercial, se for da Cemig, muito bacana, ou de qualquer outro parceiro nosso, para mostrar que esse camarada fez um papel muito importante no setor elétrico nos últimos 100 anos, mas que a gente acredita que ele pode aposentar por uma tecnologia mais robusta, mais de futuro, que consiga preservar mais os nossos recursos naturais. Na área de distribuição, a gente convive com esse cenário, né, horroroso aqui. Infelizmente, é uma tendência mundial, não é só o Brasil, igual eu comentei. O Brasil muito ainda tem a figura do gato, né, a pessoa que vem furtar energia, ou por uma condição social muito baixa, ou por uma cultura brasileira. E a gente desenvolveu uma tecnologia que vai colocar na rede aérea as fibras óticas, e por abstração vocês podem pensar, vamos imaginar que um cabo de energia tem fibra ótica na sua borda. Ok, isso não existe ainda no mercado, mas qual a vantagem disso? Por exemplo, qualquer tentativa da população de acessar a parte metálica, eu tenho que ultrapassar a minha blindagem óptica. Eu rompendo uma fibra ótica, no centro de controle eu sei exatamente onde que foi tentativa de fazer um gato. Então, assim, são essas tecnologias que a gente enxerga para o futuro, que no momento que nós estamos a gente não percebe que ela é factível, ela é possível. Então, daqui a, por exemplo, um mês, 6 meses, um ano, a gente vai conversar, vocês vão falar assim, Carlos, eu tive uma ideia, porque com a fibra ótica, eu falei, muda muito, muda. A sua ideia pode ser factível. E nesse sentido, a gente acredita que esse conceito de desenvolvimento de redes sinérgicas, ele vai aproveitar uma característica do Brasil que é de utilizar 90% das redes aéreas por causa do custo, né? A subterrânea ainda é elevada, mas aonde a gente tiver rede subterrânea, com certeza a gente vai ter a fibra ótica junto. Esse é o conceito que o CPQD está desenvolvendo junto com a gente. E só para completar, a gente tem uma grande fonte de motivação, o que a sociedade precisa. A gente acredita que ela precisa de alimento, água, energia, aí vem um gigante agora, que é a internet em banda larga. E nesse gigante, a gente vê as pessoas com muito entretenimento em casa, diversos negócios que vão surgir, que a gente nem imaginou ainda que vão surgir. Vamos dar um exemplo. Airbnb, né, que você aluga um quarto de uma casa na Europa e fica na casa de uma pessoa que você não conhece. Você pega um carro aqui na porta da Cemig via Uber, por exemplo, e aí vai, fora os que a gente não imagina. E como que essa internet, né, atua na sociedade de uma dimensão incalculável, né? Tem um lado bom e um lado ruim. Bom, eu vou ficar por aqui e eu tenho certeza que depois que se vocês verem os resultados dos projetos, a gente terá novo foco de desenvolvimento, novos produtos nesse conceito que está se apresentando aí. Muito obrigado. Eu vou chamar o Guerra, ele vai fazer a apresentação agora da USI e assim que a gente voltar do intervalo, se alguém tiver alguma dúvida, alguma pergunta, é só levantar a mão, que a gente tem microfone aqui, a gente faz um debate rápido, tá ok? Ô Marcos, você podia chavear para esse computador aqui? Gerhard, thank you very much on behalf of Cemig and our partner. We are very happy to receive you in our company. So have a good time, have a good presentation. If you if you need something, please tell us. And I'm sorry about the other part of workshop will be in Portuguese. Maybe you cannot speak Portuguese yet, but you okay.
Thank you very much, Carlos. Thanks for having the possibility to being here. Maybe next time. I've learned a little bit of Portuguese. We'll see. I want to give you a short view of the basics of DLR. If we have some time at the end, I'll show you a number of applications, but I'm not sure we are already late. We will see. So everybody knows how a transmission line looks like. So you have conductor between two towers, and at a certain time, for example, you have 20 degrees of the conductor temperature. What happens if you put current on the line? The conductor will heat up, it will elongate, and it will sag. So you know this behavior. And the line is designed in a way that at the maximum operating temperature, here in Brazil, I've learned it's 75 degrees, you are having a minimum clearance. So whatever you do, you have to make sure you are not heating up the conductor more than the maximum temperature. So to have always public safety. DLR now, whatever you do with DLR and what you find as, let's say, thermal capacity of a line, the real capacity, during operation and using DLR, this is always to be considered. Never heat up the conductor more than the maximum operating temperature. So if you look at some other parameters from the line, you see the conductor here. This is the sag. That means how much, let's say, the conductor drops to the ground, the clearance. So this sag is correlated to the tension of a conductor. You have to fix the conductor at the structure, and you need some tension to pull it. And there's a common parameter known as H/W, which describes the horizontal component of the tension and the conductor weight per unit length. And as you can see, and you surely know that the sag is corresponding to this constant H/W, and this is only, there are also two constants, that's the span length and a constant value. So sag and tension, the H here, are directly correlated. And if you want to know let's say the relationship between the horizontal and the absolute tension of a conductor, the formula is here. It's Pythagoras, more or less. This is the weight of a conductor and the horizontal tension. So you see that the tension is an important parameter during the design of a transmission line. And we will hear more about tension today, also from other presentations. So another relationship for designers, very important, a complicated formula. It has all kinds of parameters included, but the interesting thing is that this formula always results in a constant value, and it includes the horizontal tension again, the modulus of elasticity, and a number of other things. Also the conductor temperature here. So this is always constant. That means if you take the tension and the temperature at a certain point, remember 20 degrees, and you take it at 75 degrees and you put in all these numbers, it's always the same result. And so this is a relationship between tension and temperature. You can consider the other parameters as constant at the moment. So you see, if you have two different conditions, we mentioned the one at the beginning, 20, 75 degrees, so there's a relationship between the two. Practical, that means if you know one condition, you know all conditions of a conductor. And a little bit easier to understand, it's in a graph. So if you know one point between the relationship between horizontal tension and conductor temperature, you can calculate all the other points from this knowledge there. So you see, you can do that for every other point, and this gives you the complete equation, the state equation, which describes the behavior between tension and temperature. This curve is also called calibration curve of this line section or span. If you look into secret documents, you will find this expression very often, and you have to know this curve when you want to do DLR. You need to know the relationship between the two. So you would say, I know the relationship, you just showed me the formula. The problem number one is, all these parameters are not exactly known. So there are possible variation, maybe from manufacturing, like take the mass of a conductor, the conductor weight. So it's allowed to vary to a certain amount during production. What does it mean for the calibration curve of a state equation if there's a small change in the weight of a conductor. This is done for a conductor which is similar to linnet from size and weight. So what you see here, the red one was the original one, the theory. If you change the weight by 1% only, this curve moves a little bit. It's a shift. And if you look at the relationship tension to temperature, you can see it's about, let's say, 4 degrees centigrade. It's an error just because by an allowed, well, typically it's 0.5%, I think. So this is 2%. So if you take half, that's a 4 degrees. This is typically allowed to, from manufacturer to vary in that size. And look at all the other parameters we have shown. Look into things like when you install the conductor, what maybe how some inaccurate things from the procedure, from the lineman, other things like let's say elasticity of structures which change span length, things like that. So there are a lot of parameters which have an impact on the real condition of this curve. I want to show you some other behavior. This is a shift. The next one is not realistic, but I said when we change the span length from 3 to 400 meter, of course you never have this error. But I wanted to show you the other thing is what can happen. This calibration curve, the state equation, it can rotate. So it can shift, it can rotate. And if you look at 75 degrees, where you have this maximum or the minimum clearance, if you compare the tensions here, so this can cause huge error in the relationship between tension and temperature. All these small errors can sum up to a huge error. So just by relying on the theoretical curve is dangerous if you want to do DLR. You have to find out what is the real relationship between the two parameters. Okay, first summary, state equation, there is a difference between theory and as built in the line. Okay, coming back to the same picture as the beginning. So now, what does the conductor, or when does the conductor reach this 75 degrees? How do we know? Theoretically, we know when we have 75 degrees, we have reached the minimum clearance. But how do we know what the conductor temperature is? I think most of you have seen this. It's an IEEE from 1970, so 46 years ago. It's also a first or a very famous demonstration. What impacts the conductor temperature? Easy saying, it's all heat which goes into the conductor, like the solar or the heat from the I squared R, must go out or must be stored in the conductor. So there's a heat balance equation, and if you know all other input and output parameters, you can calculate the current which gives you the actual temperature, or the other way around. So there's an equation, and the only thing you have to know is all input parameters. Now, that's already the problem. What you know is typically when you have during operation, you know the current of a line, but all the other parameters are known. It's the wind speed, the wind direction, the solar. You might have an idea about emissivity and absorptivity. What you also know is the cross-section, which has an impact. So some of the parameters you know, but most of them you don't know from the line. So what conditions do you have in the line? Okay, this is what I said. When all the other parameters are known, the maximum current I can be calculated. So the conditions in the line vary, and the important parameters from weather is ambient, solar, and wind. What impact do these three parameters have? In change in ambient temperature is more or less linear in change in conductor temperature. So 2 or 10 degree change in ambient is a 2 or 10, roughly 11 degree in the conductor temperature. So that's a linear relationship. The solar radiation during summer, or typically it's between 10, maybe 12% change in capacity. In worst case, let's say in winter, which you don't have here, like snow-covered ground, there might be a reduction of, an impact of 18% on the rating. And this is typically less rating you have, 18%. But look at the wind speed and direction. So if you take an angle of attack of 45 degrees wind to the transmission line, and if you increase the wind speed by 1 meter per second, you will have 35% more transfer capacity on the line. And if it's perpendicular, you have 44%. So comparing these three ambient conditions, and this is known, the wind speed and angle has the biggest impact on the conductor temperature. For many details, you can look at the secret technical brochure 299, which in very detail describes the impact of all ambient conditions, titled "A Selection of Weather Parameters for Bare Overhead Conductor Ratings." If you don't have it, Carlos has access to that. So that means if you want to do DLR, the wind has the biggest cooling impact on the conductor. The problem is the wind is exactly the parameter which varies the most in time and in space, especially for the critical wind speeds, the low wind speeds. So how do we deal with that? This is an example, quite old example from Tasmania, south of Australia, where the inventor of a system was sitting on that lake in the morning, and you see there are dark and light parts of the surface, and it means the light part, this is absolutely calm, no wind. The dark part, there's a little bit of wind and some waves, and it causes this shadow. And if you look at these pictures taken in 5 minutes interval, you can see how this pattern of low wind speed, high wind speed completely changes within 15 minutes. And 15 minutes, 10 to 15 minutes, that's the time constant of a conductor. That means that's the time a conductor needs to react to any change in ambient conditions. So if you imagine there's a transmission line in this area, the transmission line will see within one time constant completely different conditions of wind. Another case to demonstrate the variability of wind is from a two-span section that was done in Germany. We have weather stations, or that is in Meteorological Institute which did this measurements. It was presented in secret 2003 in Australia. So they had these weather stations, and the distance of the weather stations on a tower, a suspension tower, and the met mast, which was about 200 meters away, and they compared wind speeds measured in the short distance. As you can see, this is open, flat terrain. Here's the tower with the weather stations, and this is the met mast here with the two other weather stations. So the wind speed on the transmission tower here, it's between 0 and 15, roughly meter per second. This is on the met mast. You can see there is let's say, a variation of, let's say, roughly 1 meter per second, independent from the wind speed. If you measure 10 meter per second here, on the other location you might have plus minus 1 meter per second. But that is constant. If you look at dynamic line rating, you don't care about the high wind speeds, because this resolves all problems. What is critical for you is this low wind speeds down here. And when I zoom in, you can see that the 1 meter per second wind speed on one side causes a wind speed roughly 0 to 2 meters per second on the other side, which is 200 meters. So within 200 meters, you can have a huge variation in wind speed. And the other parameter is wind direction. So if you compare the direction here with here, you can see an offset. And that's about 25 degrees. That means that the wind speed within 200 meters, the direction changes by 25 degrees. And all these values you have seen are 10-minute average values already. So this shows, I have a lot of more examples like that, that shows that wind measurement is very, very difficult to find the real conditions the conductor sees on a certain length. It changes all the time. And even if you put a weather station somewhere, 200 meters away, it might be completely different. So conclusion 2 is weather conditions vary along transmission lines with space and time, and most critical are low wind speeds. So again, how do we solve a problem? What are the weather conditions in the line corridor which allows us to use this formula? How do we get to that? The designers have solved the problem for the transmission line in a quite easy way. They said, okay, we don't know what's happening in the line, we take conservative assumptions. So the most conservative assumption would have been there's no cooling from wind. This is the highest temperature of the year, 35. In some areas we have 40 or 30 or 25, depending on where on the globe you are. And assuming, okay, we have maximum solar radiation. I think in Brazil you use 1,000 watt per square meter. If you make this conservative assumptions, you can use this formula, the heat balance equation from before, and that provides you with a value which the current or the capacity of a line. And if you use that capacity for operational purposes, 100% of time you are safe. Never a problem. But this is too conservative, especially with no wind. We know there's always a little bit of wind, and if it's 0 wind speed, then you have some convection. So the designers came up, and this is a funny story how this value came up, because it was no, let's say, no physical background, but what is used all over the world today as a, no, sorry, before I come, if you are 100% safe, that also means that you always have some wind. The temperature is never, or only a few parts of a year that high. So the real capacity would not be the static line, it would be something higher up. So all this additional capacity due to more cooling cannot be used. And in order to use a little bit of that, that's what I just explained, what the designers do today, they assume a small wind speed, which cools the conductor. So typically it's 2 feet per second, which is about 0.6 meter per second perpendicular to the conductor. That results in a higher rating for the operator, so they typically use this value for their operation. But what you can see with that assumption, there's a small risk here, which is about 1 to 2%, because it might happen that you don't have this wind speed available, and if you have lower wind speeds, 0.4 or so, you run into the risk that the real rating is even below the static. Let's say it had been looked into that for decades now, and there is only very rare situations there this really is a risk. Example, very sheltered lines which running through forests where the conductors are completely shielded by the trees, so no wind comes to the line. But in general, this can be considered as safe. But you still have this big amount of green area which you cannot use. And with DLR, what you want to do, you want to measure what is the real capacity of a line at each time, so I can use this for operational purposes. The point is, I mentioned the 75 degrees. If you follow this probability curve, this is exactly 75 degrees in that case. So when you can use all that without exceeding the maximum temperature due to the additional cooling here. So for the calculation of static rating, these conservative assumptions are used to get rid of a problem of not knowing the weather conditions, the real one. So coming back to that equation, and that is the idea where the inventor of our systems started with the development of a DLR system. I said to you that the temperature and the tension are correlated to each other. So the idea was, if I measure the tension, and I know this curve, I have the information about the temperature of a conductor. And if you remember the second slide, you also know the sag, and from that you have this clearance information from the line. So measuring the tension is let's say it's the same thing like designers do. We follow the same path. We measure this value and go to temperature and go to sag. That means we are ensuring with this measurement that we never violate clearance, it's public safety, and we never damage the conductor because we take care of a maximum temperature. So we would have a limit here and a limit tension which allows us to keep the conductor always at maximum 75 degrees in that case. As I said, the mechanical tension of a conductor, and I don't go into that, the inclination at a given point, inclination and mechanical tension are also related one-to-one to each other. So from inclination you can you can calculate the tension and the other way around. So there are two parameters which provide you direct information about sag and conductor temperature. The main parameters for designing and operating the line. So why does tension work so excellent, or inclination? So this is now a multi-span section. You have a tension, a dead-end tower here, and here you have suspension towers in between. You have variability of weather in a span. We said about 200 meters, can be 50 meters, but you also have variation from span to span. So there will always be areas where the conductor will be hotter because maybe sheltered, maybe no clouds and sun. On other parts, there might be some clouds, or there might be heavy wind or strong wind. So this part of a conductor will elongate and sag, as I've showed at the beginning. But the line design, especially this design with this insulator strings, is exactly causing a movement and equalization in the section. So what happens in that case, because the background is that the tensions are not in equilibrium here at this point, so that causes these insulators to swing in a certain direction, and at the end you have this constant horizontal tension along the whole section. So that means if really something happens here, due to the equalization, the tension will change at the end of this section. So the tension measurement is a kind of integration of all the events, the weather conditions happening along the section. The same you could measure on the other side, but it's not necessary. Typically, or in general, we are measuring the tension on one side and getting the information of all weather conditions in this area. And designers are designing a line exactly like that. They assume the average temperature causing a certain condition, and this behavior will be safe. So in that case, there will always be enough clearance in each of the single spans. So you can say what we are doing, we're using the conductor itself as the hot wire anemometer. So the conductor temperature locally is exactly what impacts the tension. And the average of this local impacts results in a tension. It also has an impact on the inclination on a given point. Here, wherever you put this sensor measuring the inclination, it has the same possibility as the tension. With this change in inclination, you can identify the conductor temperature and the sag condition in that section. So the tension and inclination provide the information from a whole line section. And this is a difference to what we in SECRE are calling point measurements. Point measurement would be a weather station or the measurement of a conductor temperature at a single point. These two parameters are kind of distributed measurements along the line sections. And if you look into the SECRE TB 498, I think it's in it, dealing with dynamic line rating, it says that these type of measurements are the most accurate way to determine the conductor condition. Okay, now, how do our technologies look like? With USI, we have two different technologies. One is what we call the CAT1. It has been used within CEMIG before. This CAT1 is based on tension measurement. So we are measuring the mechanical tension between the insulator strings and the dead end cross arm on two sides, so measuring in two directions, two line sections, where we have different sizes of load cells for different mechanical requirements, and so we have special protecting against lightning since 10 years now to avoid damage through lightning strikes mainly. And these load cells, this is from Switzerland in the Alps. They use two load cells instead of one because they have two connections to the cross arm. So this sensor is giving the information to a base station. The base station has some electronics, it has a communication. We have an additional power box with solar panels, batteries, and the information is sent from this base station into the control center. Another sensor we have, and I will not describe in detail, is what we call a net radiation sensor. You can consider that as a piece of conductor which you just install parallel to the conductor, and this has the same diameter, the same emissivity, absorptivity, it has roughly the same time constant as the conductor, and I said it's installed parallel to the conductor at the same height on the tower. So when there's no current on the line, this sensor gives us the conductor temperature. So the unloaded conductor, the non-energized conductor temperature would be the same as this sensor. This has some very good results in for calculating later on calibration or state equation for doing rating calculations. It's a very, very tricky approach to avoid a lot of other input information you would need in the other way. Okay, so this is also going through the main station to the control center. And this is a, let's say, a schematic scheme how the Cat1 system works if it's using radio or fiber optic communication. In the transmission line, we have a number of installation points. We have in the substation an RTU we call Cat Master. It's a data concentrator. It takes the measurement from various measurement points. It has a protocol converter, so it talks EMS protocol on that side. And we are sending the raw data into the control center, where we have a software called ICW, which does all the rating calculation, the checks of data, the communication, security checks, and at the end, the results are sent to the operator screen. So this is a fully integrated solution where the operator has the real-time information about the impact of weather conditions on his on the rating. So instead of static rating, the operator now can make use of the real thermal capacity of a line. The power donut, you have seen it before with Carlos. It's installed directly on the conductor. It has quite the new version, which is out since 3 years, has quite a lot of sensors included the device. I talked about the inclination, so it measures the angle of that point, and this angle can be used to calculate the tension and do the same procedure as with a CAT. It also has a local temperature sensor. Dying? Oh yeah. I think Carlos, I don't understand, mentioned it. It has 2 temperature sensors directly measuring on both sides of a conductor and taking the average of the 2 values. This donut also measures current and voltage, so we can we don't need the current from the SCADA system. We measure it ourselves. And what is included, but where the, let's say, the applications are still under development, we have accelerometers for 3 dimensions to, for example, making frequency swing measurements of a span. The communications, the donut itself has cellular communication or kind of ZigBee short distance communication included. Powered by the conductor itself. And if you want to do DLR, you have to add additional weather station to the system. We need one more information than the inclination. This donut has been used in Brazil quite a lot in the past. I think we will hear more about that later. Regarding communication, this is from an old presentation 3 years ago at ONS. So the donut communicates cellular to a server somewhere in the control center or wherever, and it communicates ZigBee with the weather station. So the donut is used to communicate the weather station information to the server. With a donut, we can do the same thing as with a CAT. We can install a ground station. The ground station is a combination of a weather station and including additional communication. So if we communicate from the power donut by ZigBee to a ground station, we can go from here with radio, fiber optic, or any other, maybe a satellite communication to away from the field to a server. So the structures of the 2 technologies are similar with some advantages for the one or the other depending on what is the condition in the field. So now we are at the beginning, we have the measurements, tension, inclination. Alternative, if you have the possibility to get the sag, you cannot measure it, but if you get it from somewhere else, maybe from clearance measurements. So starting from that measurements, we can determine the average conductor temperature, and for doing that, that's what I mentioned earlier, you need the calibration of a line section. So that means you have to find out what is the as-built condition, the relationship between the two parameters. This is done in our case by using our field measurements. So from the tension, from the temperatures we are measuring with a special sensor, or from the inclination and weather data, we have a very, let's say, excellent way or methodology to determine the real condition of a transmission line, the relationship. And it has been tested and verified by a number of customers that this, what we are doing here, is very accurate. One of the customers was RTE in France. On their pilot project a number of years ago, they went out and verified what is the real conductor temperature and what is the temperature which was based on tension measurement. And they have looked at 4 different spans in the line, and you see at different times and dates. So within 3 weeks, they went out 3 times, did measurements, and compared the, sorry, this is in French, what you hear, but I think you can understand it. So they found that the temperature of the conductor, which they found in their survey, compared with the temperature of a conductor from the tension measurement, the error was in the range of maximum 2 degrees centigrade. I don't know any way how you can get to, well, maybe if you put a fiber optic into the conductor which measures continuously along the section, I would, and that's our experience, this is the tension with the accurate calibration is maybe the most accurate way to determine the average conductor temperature, which sounds strange, but it, as you might remember, all these weather impacts, which makes it difficult to get the local conditions. For operating purposes, only the average conductor temperature is necessary, and this is an excellent way of attention to get to that point. So now the next step, because the average temperature doesn't tell a lot to the operator. The operator does not work with temperatures, he needs currents. So we have to get from the conductor temperature to the thermal capacity of a line. And this requires another step here in between, which I, between this, the other arrow there, which is, I will not explain in detail, but it's called, you have to determine the effective wind speed, or one effective wind speed, I would say. So what is that? You can find more about this definition and how to do that in the secret brochures. What we are doing, just as an idea what we'll do, we have certain measurements. So we have this, just an example here. Let's say the conductor temperature without current, you know we have a sensor there, is 30 degrees. From the tension and the calculation of a conductor temperature, we know the conductor at the moment is 75 degrees. So in Brazil, that would be already the maximum. In US, in this case, they can go up to 100 degrees. So that means there is still some buffer. The 75 degrees has been caused by the current, which is on the line, and by the ambient conditions. So if you take your design parameters, that means 0.6 meter per second, 35 degrees, you take the current, which you know, you will end maybe at 90 degrees. So the real conductor temperature is less. That means you have lower temperature, higher wind, whatever, you don't know. And you will never know what exactly has caused, which were ambient conditions, has caused the whole thing to go down to 75 instead of a 90. What we'll do, we say, okay, we keep everything from the design criteria constant, we just vary the wind. So we assume the wind is not 0.6, but, and then we look what wind is necessary perpendicular to the conductor to create the 75 degrees. So let's say maybe 2 meters per second wind speed you have as an average along the line. So that would be the effective wind speed, and it includes temperature variations, maybe rain or something, or whatever ambient condition has an impact to result into the 75 degrees is packed into one parameter. So if we now know the effective wind speed which has caused the temperature increase to 75 degrees, we can use the same effective wind speed to say, okay, now we want to have 100 degrees. What is the additional current we can put on the line, assuming we have the same effective wind speed for this green part. So that is very roughly the explanation how we, with our measurements, and this is very specific because we have these very accurate two values from our measurements, which allows us to also very accurate calculate the actual thermal rating of a conductor. So now that is, I would say, the procedure, more or less, how to get from how to make a decision about measurements, how you methodology to get to the final rating. Beside the choice of a sensor and the methodology, there's a third part which is important for DLR, the configuration. So assume you have 100-kilometer line, still you have a question, where do I put my sensors? You don't put them in every tower. So there's it's not I wouldn't say it's programmable. What we'll do, we look at many things to come up at the end with a recommendation of where to put measurement points, tension or inclination, so that we make sure we cover all critical areas for all possible weather conditions. If you just assume a line has a 90-degree angle, depending on the wind direction, there will be critical sections in different part of a line. So this is a very important thing, because all that, what you have before, is not enough if you don't measure at the right spots. And you don't want to measure at each spot. So we have 20 years of experience of that, and we have been proven in a demonstration project in a whole area that our methodology to find the right places is more or less 100% correct. So there's a study which is public, and if you want to read more about that, I can give you the link to that. Experience. So USI has owned the power donut since '91. So that's 25 years ago. They acquired the original version, and since when it has been improved up to the last release PD3. The CAT1 was developed also 25 years ago, 91, under the company named the Valley Group. So it was until 97 we had we have now Series 4, yeah. So until 2007 it was private owned, this company. That then was acquired by Nexans. The inventor retired, so he handed over the whole business to Nexans, and as you can see down here, 2016, USI also acquired the CAT1 technology from Nexans. So you see there is 50 years of history, and In reality, like in practical, the engineers from CAD 1 moved all to USI. So there are some engineers who are in the business doing only DLR for 20 years on both parts of the technologies, USI and with Donut and CAD 1. I've been involved in DLR or just doing DLR since 98, that's 18 years ago. And I was, since we were acquired 2016, I was covering the European market so far. Installations, CAD 1 in the 25 years we have more than 500. You see the majority are North America, Europe, and we have some very strong business in Australia, and I've just been there. We have CADs installed there since 20 years, still operational, with several utilities. Unfortunately, or it's good, we don't know. So they're still operational, that's a good thing. With a Power Donut, looking at the last release, we have about 120 from the last version, but there have been more than 1,000 Power Donuts from the first generations. So there's also a huge practical experience from the two technologies, and this practical experience results in, let's say, more development, more knowledge, and we put that into our software. So there's a permanent improvement from what we get feedback from the customers. And that goes into our system and our methodology. Maybe 5 minutes? Oh, that was the basics. I have some applications. Just at the end, we will not go through all of that, but you can see there's a huge variety of possible applications. Maybe something typical. What does the operator get from a DLR system? What the operator sees, what he sees anyway is a current on the line, so he knows what current is on the transmission line. The red one is the static rating, which is based on the assumptions we talked before, and the upper line is a dynamic line rating. In that case, it was from the CAD 1. So what you can see on this 24-hour plot, at 10 o'clock in the morning, there was something happening at contingency, and the current went up and even went above a static rating. So for an operator, that means when the current goes up to the static rating, he has to redispatch, he has to react. In that case, he was looking at what is the real capacity of a line. It was much higher, so that means although he was at the thermal or the static rating, the conductor temperature was not 75 degrees. The 75 would have been with his dynamic line rating, so that means he could just wait and see how the current goes up without violating any clearance requirements. So in that case, it took 3 hours to solve a problem, and the current went down again. And the operator, let's say, solved the problem just by doing nothing. So a lot of people think DLR makes more work to the operators, but in practice it's just the other way around. As you can see here, instead of doing some switching, the operator just has to look at the whole thing. I talked about risk, about the risk of a static rating, and you can see here on that day in the late afternoon, 5:30, the dynamic rating was even below the static. I talked about that, low wind speeds, and this is very typical for early evening. The wind dies. So there was extremely low wind speed at that time, so this event in the evening wouldn't have helped at least it would have helped the operator to know there is no capacity. So that is a typical case where the rating was used without, let's say, violating any standards or requirements from the system. And it also kept the grid in its predefined most optimum condition. There's another case where the dynamic rating was installed but not used. So it was in a test phase, and what happened here is there's some conductor temperature. You see the red line here. This was the conductor temperature without current. This is with current. This is a load here, and this is a DLR and the static rating. So you see here, there was a peak. It doesn't say the time, but this peak on the left-hand side where the current approached the static rating, and without using the DLR on that line, the operator had to redispatch and get the load down in that case. You see there was some headroom, and also the rating was increasing here. So he might have survived with using the DLR, we don't know. But for sure he would have survived later when this next day the same peak came. He still had to redispatch, but you see it was the next day how much capacity was available on that line. So in this case it shows it again how you can avoid activity from the operator. Yeah, as I said, I have a number of more. If you have any questions, and I'm happy to show you more about how to use DLR in the control center. Thank you.
Agora é o horário do intervalo, mas se alguém quiser fazer uma pergunta, alguma coisa específica para o Gerhard, a gente pode traduzir para o inglês, né? Se eu conseguir traduzir. E na programação original tem uma parada para café e água. Por enquanto a gente só tem água, mas se alguém quiser tomar um café, é só entrar dentro da sede da Cemig, eu consigo mostrar onde está o café ali dentro. Então é isso, a gente vai parar um pouquinho e se alguém quiser fazer alguma pergunta é agora. Então a gente está colocando só um momento. Você se apresenta, por favor, e faz a pergunta.
Bom dia, eu sou o Victor Diago, da empresa Minipa. E I would like to ask, when you mentioned that you can pick some metering points over the temperature on the cable conductor. In theory, if I can have the real metering of the environment temperature, and I can also have some measurement of the temperature of the cable conductors over a few kilometers, I can get to a closer estimation of the overall temperature of the cable conductor. In that case, I would need to have two different metering. I mean the environment temperature and the cable temperature over some points. If I have this setup and I have these two measurement points, how can you see that the wind can affect in the, I don't know, between the metering points in a way that will cause a huge difference over the meter temperature? I mean, if I can estimate the temperature over some measurement points in my cable conductor, will the wind or will any other environment factors cause a too much drift in my calculation? How can you see that when we talk about wind and temperature?
Yeah, that was is one of the main questions we looked at, because if you have measurement points, the question is how many points do you need so that you have, let's say, as an average of this point measurement, the average conductor temperature. This again depends a lot on where you are, and if you do some measurements, you can afterwards you can say yes, let's say 4 measurement points in a span is enough, or you might say, okay, if I measure at a certain point, this is a representative point for the span, but you need to do measurement first. And I haven't talked about very sheltered areas where I have also some plots. That in that case, it looks like you need like 6 or 8 points in a span to have an average result of that. If you're an open flat and nothing happens, you need less. So let's say the amount of information you need is difficult to get. The secret brochure made it very, let's say, very compromising. Is that okay? You need, let's say, 4 measurement points. I think that's a recommendation. And was it 299 or 498? At a minimum, because there's no way to say how much you really need. With this, if you have let's say, if you have a fiber optic in a conductor, OPPC or something like that, it gives you, let's say, within every meter a measurement point. So this for sure gives you let's say, a very good information. What you need for operational purpose is the average. So it's nice to have it. You don't look at the peaks. Nobody wants to know it, but the average. For big conductors, there have been tests. You put a fiber in the steel core, ACSR conductors, you put a fiber on the aluminum layer, and you compare within the 2 layers. There can be changes up to, let's say, 4 degrees within 2 layers. So there's a variation. That's locally. If you take the average, it's better. So this gives you an excellent information about temperature, no doubt about that. The problem is, that doesn't tell you what sag you have, because the temperature doesn't say where the conductor exactly is located. So if I change the sag manually, the temperature stays the same, but you don't see it. And I have cases from our measurements, it's named creep, but there are other impacts which change the conditions in a section. So with a temperature, you miss that. That means if you use temperature, it's an excellent start for the temperature, for conductor, but then the utility has to go out and does, let's say, a regular survey that the design of a span hasn't changed. So that is, let's say, the disadvantage of a temperature. Otherwise, the temperature measurements like that could be very accurate, yeah. And with a point measurement, it's kind of unknown how much points you need. You're welcome.
Thank you.
Alguma questão a mais? No. Okay, thank you very much. We have a good presentation. Ok. A próxima apresentação vai ser às 11 horas. O professor Rene e o Douglas vão preparar aqui. A gente tem um banheiro ali, tem um bebedouro. Quem quiser tomar água é só me avisar que está dentro da Cemig. Quiser tomar café, é só ir lá dentro da Cemig. E então nós vamos preparar aqui a próxima apresentação e fique à vontade. 11 horas a gente retorna.